Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our exercises on vector velocity. On velocity, speed, and acceleration using vectors. Okay, so let's proceed to number 7. I think the last one was 6. Okay. So for number 7, we're being asked, um, we're actually given a scenario here. So we have a force. This force has a magnitude of 25 newtons. So it has a magnitude of 25 newtons, which acts directly upward. So it goes up. So directly upward. Oh, from the XY plane. Okay. Uh, so it's acting on that object, on a particular object, upward the xward, upward from the XY plane, and this object has a mass of 5 kilograms, right? And here we say the object starts at the origin with an initial velocity. So object. So some force is acting on an object. I think it's pushing or pulling that object. So the initial position of that object is the origin with initial velocity. So let's just say V naught. And this initial velocity has, oh, so it's a velocity vector, and its parameter is when it's 0. Okay, I'm assuming it's t. And this is I minus j. So let's quickly translate that. I is 1, 0, 0. I subtract that with this vector, 0, 1, 0. And so I get 1, negative 1, 0. Okay. So it's just a translation of a problem at my own convenience. And here we're being asked to find a position function. So I'm going to be specific. I want to find, or the problem's asking me to find a position function. We're going to call it R of t and its speed. And so that's my R prime of t. And we get its magnitude. Yeah, that's it. At time t, so at t. So how do we do this? Well, we're given a force. So here's what we're given. We have a force with this magnitude. So we have F is equal to 25 newtons. And it acts upward. And we know force is a vector, right? We're also given a mass. And I'm assuming this mass is constant, which is 5 kilograms. And this object starts at the origin. So it starts at v of 0 with this vector here. And we're being asked to find its R of t. Well, I guess one way we can do this is to find its actual force vector, right? So here we're saying that force is a vector. What else can I say about it? I can also find its acceleration, right? Because force is equal to mass times acceleration according to Newton's second law. And so 25 divided by 5 is 5. My acceleration is 5 or something like that. Not particularly sure. Right, let me double check. Okay. Oh, so we do translate our force as a vector. So what we're saying is if we're given a 3D space, where we have our x, y, and z axis, we're saying that this force vector has a magnitude of 25n, and it acts directly upward from the xy plane. So from the xy plane, meaning it's there, right? And so this force vector is actually 25k, right? Because it's acting upward from the xy plane. And what else can we say? The object has a mass of 5 kilograms. So that's another thing we can say. And then from here, we can actually get our acceleration, right? Because force is equal to mass times acceleration. And so that's this vector, which is equal to mass times acceleration. And we also know acceleration is some vector here, right? So let's just say that this is a of t, where it's a vector. What else can we say? Well, here we can actually translate the problem a bit. So this is where it's actually good to use IJK, apparently. So we say 25k is equal to m a of t, right? So we can say that. And actually, this m is just 5. And if we divide it, well, we get 25k over 5. We treat it like an algebra thing. So we get 5k is equal to a of t. And so that means a of t is just 0, 0, 5. So these are the instances where it's actually good to use it in terms of IJK format, right? And then from there, we want to get our velocity. And then that's how we're going to get our position function as well as, oh, we can get the position function. So that's another thing that we're going to try. But we can get the speed. We can get the speed. So, okay, let's take that. Let's integrate. I'm going to integrate real quick. So my idea is to get VFT. So I want to integrate my um, my acceleration vector. And so I integrate its components here, right? So, well, what happens here? Well, these are just zeros, basically. Because even if I put them outside, I get 0 times t plus c1. It doesn't really matter. Or does it? I don't think it does. Yeah, because there's gonna be 0 either way. Um, but yeah. And so well, I guess, I'm not used to this. I mean, okay, let's just go through the long cut just to be super, super sure. So I'm gonna integrate this one. I'm only gonna do it once just to make it easy for myself. I have a 1 here, right? Then I do t plus some constant. And this is apparently supposed to be, I don't know what it is. Because, okay, this is weird because it says here it's 1. So even if honestly, if I plug in anything here, or no, I plug in a 0, I'd still get C1 is equal to 1. So I'd actually get some constant value here if we're being, uh, yeah. And then let's try the other one. I mean, this one's just the other one. Okay, I find this a bit confusing. This one's just 5t, right? And here we find the constants. So, how's that gonna go? Well, we got 1, -1, and 0. We plug 0 for t. And so 0 of 0 plus C1 is equal to 1. And so here I just say my C1 is equal to 1. Then I have my 0 times 0 C2 because I have this other, my Y component. And this is going to be, well, -1. So my C2 is -1, right? And lastly, I think it was 0 here. So I plug this in, 5 times 0 plus C3 is 0. So this makes my C3 equal to 0. And from there, I now have my velocity vector. My velocity vector has components 0t, so it's just 1. 0t, it's just 0. So C2 is -1. And then lastly, this just makes it, well, 5t, right? This is the only one that doesn't affect it. Okay, so that's my velocity vector there. Great. Now how do I get I can get my speed, although I'm not sure how to get my R of t. That's another issue. Unless I have a formula for it. I'm not sure how to get my R of t. Okay, but I can get my speed here, right? Because I just get my absolute value of my velocity. 1 squared, 1 squared, 5t squared. And I'm gonna get something like this. 1 plus 1, that's 2. So I'm gonna get 2 plus 25 t squared. And I think I can simplify that. That's it. So that's my velocity or my speed. I mean, yeah, this is tricky. This is tricky. I guess I can. Oh, I just realized something. and it wasn't obvious, I can actually get my RFT. You know why? Because I have this info here. Object starts at the origin. And so what does that mean in math? In math, if the object starts at the origin, at r of 0, it starts at 0, 0, 0. That's what it means. So yeah, this part was, not super obvious, right? Okay, now let's quickly solve for it. So my RFT, so again, I go through the same process. I take the derivative of my velocity vector. So what were the components? Okay, I integrate 1, I integrate -1, I integrate 5t. So integrating these are actually super easy. I don't want to be too cocky. I'll still do it one by one. So usually in math, if you've gotten the pattern of something, you're good. You don't have to make it complicated. Okay, so this is t plus c1. Then we have -1 dt over here. This is negative t plus c2. Really as simple as that. Now we have my 5t here, which is just, well, it's 5t squared over 2. So I did mental it a bit. And now from here, I get my constant. So at r of 0, I'm at my origin, right? That's what it was saying in English. So I plug in 0 for all of them. And so my C1 is 0, negative 0, minus 0, plus C2 is also 0. So my C2 is a 0. And lastly, my 5, plug in my 0, plus C3 is also a 0. And so this means my RFT is just this t, negative t, 5t squared over 2. That's it. Done. Since all my constants are 0, I don't really care to put them in. And I also forgot to put in my speed at time t. I think that's it. Yeah. Okay, I'm just gonna plug this in, see what happens. So that was a bit tricky. 5 over 2 t squared. That's fine. Doesn't matter. T minus t 5t squared over 2. And then my magnitude is the square root of 2 plus 25t squared. Okay, let me hit submit, see what happens. Nice. Okay. Number 8. We have what? 4 more problems to go. We can do this. So here I'm being asked to find the tangential and the normal components of my acceleration vector. So I'm just going to say A of t, right? So I'm asked to find, okay, let me just, A of t, A sub t, and A sub n. So this is me just highlighting what the problem's asking me to do. And here's my given. I'm given a position vector. I'm gonna immediately write it in vector form. I don't like it in IJK format. I can translate it if I want to, but for now, I don't think it's needed. T. Also, I'm more comfortable working in this way. Okay, so first, well, we already have formulas here actually, so let's just do it. So we find A of t. So our formula for that, which I'm gonna highlight in red. So A of t is just equal to what? Do I have it here? Probably have it in my notes. So that's something I would put in a cheat sheet during a test. Where did I put it? There you are. R prime of t, the dot product of its second derivative over the magnitude of r prime of t. So it's, just to reiterate, it's r prime of t, the dot product of that with its second derivative over the magnitude of my first derivative. Okay. So before I actually do that, let me compute these values. So I'm going to compute its derivative. This is just negative sine t. This is cosine t. This is 1. Then I compute its second derivative. So this is negative cosine t. This is negative sine t. This is a 0. Okay. I guess I could compute for dot product. Not sure if I need to do. Okay, I guess I could. Yeah, you know what? I'm gonna compute it like right now. Okay, let's compute my dot product. Uh, Actually, I should have done it. Oh, okay, I'm thinking of a way on how to organize this more nicely. Okay, I was thinking maybe I could just switch this down here because it knew that I was computing for that. And then for this whole thing, I can just put it up here. There we go, much better. So here I find A of t, so I compute for these missing pieces. Okay, so I got my dot product. Uh, Usually this would be easier without the these and that. Okay, just has to find there. Okay, so I just go for it, I guess. So I multiply my sine of t and my cosine of t. Then I add it to my, oof, this is, I add it to my cosine of t times my negative sine of t. So here I'm just doing a dot product basically. And then this one's just a 0, so it doesn't matter. Uh, there was a formula for that, where if I compute a sine and a cosine together, and they have the same parameters, so I'm just gonna, this is trig identity. But if I get sine x and cosine x, I basically get 1/2 of sine 2x. So here in this case, well, if I get negative sine and negative cosine, they just turn positive, so I get 1/2 sine of 2t. And here I add, here again, negative actually. So I guess I make this one a negative. And if I get rid of those signs, well, I can just multiply cosine t and sine t. And I should get the same thing. So now I have a 0 for my dot product. I don't even care to compute the other thing. Because if this is 0, well, why would I care about this, right? Well, probably for the other one, but yeah, this is 0. So I'm saying So this is 0, right? So I just subtract two similar terms here. No, two, it's not even similar, it's the same terms. That's why it makes it 0. Yeah, okay. Then I compute for, here my normal. So again, there's a formula for this. And I think it was, let me see if I memorized it. But I would put it in a cheat sheet though. I think it was the cross product. And I divided by its magnitude here. I think that was it. Oh crap, I got it. What the hell? Yeah, that's it. Okay, don't ask how I did it. So here we do a cross product. And then we compute the magnitude. So let me just do a cross product here. Okay. My R prime of the S components. Oof, this is long. There we go. Much better. So here we have negative sine t, cosine t, cosine t. And I think that was 1 for my first derivative. Yeah. And then for my second one, I have negative cosine t, sine t, 0, right? Oh, this is a negative sine. Okay. I can see that. Okay, so computing this cross product, I take out all my i's. So I get cosine t times 0, that's obviously just 0, minus negative sine t, so that's plus sine t. How much shortcut? So this is sine t. Of I. I subtract to my j. So I take out my j. This is 0 minus positive cosine t. So this is minus cosine t for my j. Then I add it to my k. So I take out my k's, I get what? Negative sine t times negative sine t, I get, well, sine squared t. I get sine squared. I subtract that to my negative cosine times cosine, so I get a negative cosine squared. So it's actually plus cosine squared. And oh, look at that. That's 1. There's a trig identity once more, so I get 1. I get k. And then pretty much all I get here is this vector here, which looks really nice. There we go. What else? I get the magnitude, right? So I put them in a square root. I get the square. I get each component squared. Okay, let's. Okay. Here I get sine squared plus cosine squared. I get 1 plus 1 squared, so I actually just get square root. Okay. What else? I get my magnitude of my first derivative. What in the world is this? So this is this one. We square all of them. So my first component squared, my y component, or my second component squared, my third component squared. Did I get it? Sine, cosine 1. Negative sine, cosine 1. Okay. This is sine squared plus cosine squared. That's 1 plus 1. That's actually also square root of 2. So my normal vector in this case is just 1. Or my normal component of my acceleration is just square root of 2 over square root of 2, which is 1. right? Because I just divide these two. Yeah. So it's a 0 for my tangential and a 1 for my normal. I genuinely wish I had an explanation for this because this looks really cool to analyze. Yeah, I generally wish I had an explanation for this besides just plugging it into random formulas. Uh, I'm actually gonna see if there's an explanation. There should be. I hope there was a visual somewhere. Um, yeah, I want to know. Okay, actually, let me search for an explanation. I'm not gonna. Yeah, let me just search for an explanation here. So apparently, this position vector, the given position vector, is actually a helix, right? Um, yeah, I could. Yeah, I want to see a geometric intuition maybe. If we're in a helix, right? Our tangential vector, let's say, is at 0. And so if it's at 0, then speed is constant, right? Because that means we're not changing the magnitude of velocity. And so the direction does change. The acceleration is purely normal. Also, it's a centripetal acceleration. So kind of like the centripetal force that we talked about earlier, where it kind of goes down. Um, yeah. So kind of like uh, if this was part of our helix, imagine that's part of the helix. The helix looks some things. But if that was a part of the helix, right? Let's say we have our tangential vector there. It's tangent here. That means this is 0 because our derivative is 0 here. If the slope of this is 0. And if we have our normal vector here, that means they're perpendicular. Um, yeah, this is 1 because direction changes constantly. So if it's actually like here, if my uh if my particle if my particle, this black particle, is moving right there and it's exactly at this point, then it's going to curve if my normal vector is pointing downwards, then it's going to curve pretty much. This would have been nice if I had like a visual, but I don't. I don't know how to put visuals. Um, but yeah. Okay. Moving on. Let's see another example. Number 9. Again, we're being asked to find tangential and normal components. So same idea. I'm just gonna copy paste. Damn, I wish I had an example. Uh, yeah, the tangent and the normal. So something like this, right? They're perpendicular. This is my acceleration, this part. These are the formulas. And we say that my tangent is just the derivative of my speed because we're analyzing how our speed is changing, right? Are we accelerating? Are we decelerating? That's calculus 1. And our normal is the curvature, how much it curves, times speed squared. So we square our speed, we multiply it by the curvature. Curvature just tells us how much our particle, as it's going through or as it's moving, is curving, right? So curvature tells us how much our particle is curving while it's moving. So the bigger the number, it's curving a lot, right? So yeah, that's something that I think should be, no, it's not intuitive, it's physics. Uh, but this helps us analyze motion because we get to analyze its tangent and normal components of the acceleration. But yeah, I've heard you can do some cool stuff with this, or so I've heard. But yeah, that's really all the definition is. Like this tangent just tells us how our speed is changing, and then this green normal component tells us like how much are we curving, right? So if we're extremely down, uh, say my normal's here. Let's say it's here, right? So our particle is moving, it goes there. Let's say this purple is my path. Oh, this purple thing here, that's my path. This is my normal. And so my tangent is probably here. That straight line to the right. That's my tangent. How do I know? Because it's perpendicular. So yeah, here we're pointing extremely downwards. So this means we have a tendency to really curve, right? Yeah, that's the best I can give. So as of now. But yeah, if you guys know more about this stuff, please do tell me. Uh, but yeah, okay. So we find the tangential and normal components of our acceleration vector. Here we're given a position vector. I'm gonna make it in vector form because I want to. So my axis, my x component is 6 plus t. Oh, so this is now in 2D. Then my y component is t squared plus t. Oh, my bad. T squared minus 2t. Cool. Now we find everything we need to find. So let's find my first and second derivative for now. Actually, also my speed. Let's find my speed. So my first derivative or my velocity. So this is 1, 2t minus 2. That's it. And my double derivative. My second derivative is just 0, 2. That's it. And from here, now what? Yeah, now we can find what we need to find. No, let's find the magnitude of my first derivative. So this is a distance formula from the origin. Of course, everything is going to be in the origin. There we have it. I can simplify, I guess. I'm going to leave it as is because I don't want to mess it up. I'm going to leave it like this in that form. Okay. What else? Yeah, I think that should be fine. I guess we find a of t now, right? So here we need to find the dot product of my first and second derivative. So let's quickly do that. So this is going to be, what's this? 1 times 0, that's just 0. And I add that to 2 times 2t minus 2, which is just 4t minus 4, right? Yeah. Okay. There's a scalar, it's a number. What else? Oh, that's it. So my AFT is just my dot product over, what was it? Over my speed, right? Yeah, over my speed. So it's this magnitude of my r prime. Square root of 1 plus ut minus 2. And I square that. Done. Easy. Now I find my normal component. So here I find the cross product of my first and second derivative. So this is the, I think out of all of these, this is the hardest one. Okay, so I actually only have ij here. So I only have ij. Okay, so we get 6 plus d, and then, oh shoot, where was I? Oh, no. 1, 2t minus 2. Let me just do it. 1, 2t minus 2. And then, oh, where am I? 0 and 2. And then here we immediately do a cross product. That now you know why we call it a cross product, because we're literally doing a cross product. I just realized that now. That's so funny. Okay, so I mean, I guess I do it for my I, right? Actually, I'm gonna be honest. Let me quickly Google how to do it when I don't have my K, because I don't know the procedure for doing it without K. But yeah, how do you do a cross product with only 2? Vectors with 2 components. Yeah, how do I do that with 2 components? Uh, oh wait, I can't do a cross product for 2. What? Uh-oh, really? I can't do that? Uh, only 2 components. Yeah, I just realized I don't know how to do that. Oh, there's no 3D cross product. Oh crap. The 2D cross product really a scalar is 8 what? A1 times B2. Oh, so it's just a 2D cross product. So I basically just multiply them like so, and then I get something in terms of, I get a number. Huh. So I get a number here. That's surprising. Let's see what we get. But basically we have to multiply these two. 2 times 1. We subtract that to 2t minus 2 times 0. It's really just 2 here. For my I, okay, let's do it like normal maybe. Maybe if I do it like 2i. Yeah, so let me do this times this for my I. And for my j, it's also this and then this. So it's the same idea. So we have 2i and then minus 2j. Not sure this is right. Then I got 2 negative 2 question mark. And then I'm gonna try to see if, so the properties of a cross product, right? If you get the 2, if you use the dot product on both of these, you should get 0. So let me just quickly try that. I add it to Yeah, let me just quickly try. 2 minus 40 plus 2. So I get 4. What? Is that possible? R prime? So clearly this is not a 0. Hmm. Okay. Try the other one. The other one looks plausible. So I do 0 times 2. I added the times negative. So no, it doesn't work. How in the world do I get a cross product here? Um, uh, A sub D, A sub N in terms of, yeah, I'm using a, oh, okay. That is something. Yeah, because I gotta do here. Uh, does that does that make sense? I don't know if that makes sense. You know, because I can't get a cross product of a scalar and a vector. Or am I missing something? I feel like I don't know. I feel like I just realized this is tricky because I haven't done a cross product of two components before. So I just realized I don't know. Um, anyway, let me because it's a scalar. Yeah, you're right. Um, but is it? Mm, mm. Okay, I'm gonna check if it's. Yeah, I mean, I can't really. Yeah, I'm gonna check it. I'm gonna see if it works. If it works, then we got it. If it doesn't, then it's probably something else. Not sure how it works in this case. But yeah, it's we're gonna have a scalar because it's a 2D. Apparently, that's the case here. Um, let's try. So I multiply 2 times 1, and I subtract this 0 times this, and I basically get 2. So my A of n is, oh no, oh, then I get my magnitude here. So I get R of this, and so the distance of this to 0, right? The distance is just 2. I could say like what, 2 squared and still 2. Yeah, I could honestly just say, okay, I got it here, right? Okay, I'm gonna put like a quick note. Uh, I'm gonna put like a note here. The idea is cross product into the gives me a scalar. So it doesn't give me a vector. So I can't really use that to compute for a dot product here, right? Okay, let me, what else can I do? Oh, I'm just gonna plug it in. So my A of n is now my cross product of these two vectors divided by the magnitude. So this is 1 plus, yeah. So a little bit of a hump there, but okay, let's see if we got it actually. I want to see. If we did, then okay, cool. That's how it works in 2D, I guess. Okay, so my tangential component is 4t minus 4. 4t minus 4, and I divide that by the magnitude of my velocity vector, or my first derivative of my position vector. So that's 1 plus 2t minus 2 squared, right? Okay, let me just quickly double check to see if that works. Just a quick check. Okay, got that. Now my normal my normal component's a little weird because I got a scalar for the cross product instead of a vector. So we'll do the same thing. So for my cross product, I put a scalar. And I put, as my denominator, I put the magnitude of my r prime. Okay, let's see if we got this actually. I'm not too confident, but we'll see. Oh, so we did get it. Okay. So this is, yeah, so it actually gives a scalar. And we just have to deal with it. Okay, cool. Uh, okay, okay. Right, we have 2 more questions here. So this one's a bit tricky. Well, that one already was tricky. Here we're given a projectile. So now we go into projectile motions here. And this projectile is fired with an angle of elevation A. Or not A, alpha, I think. Right? And its initial velocity, which I assume is a vector. It is a vector because it's in bold. So I'm just going to write it like that. And then we have a figure here. That gives us the initial scenario. Okay, so let me quickly do this. So this is the scenario that we're given, right? Okay, now what's it asking? Here we assume that air resistance is negligible. When it's, okay, so we did go through an example of this. When it's negligible, meaning we don't include it in our projectile simulation. So here we make some assumptions. We assume that air resistance, I don't know, like wind, like tornadoes and such. Nuclear, okay, it's not. Negligible. My spelling is negligible. Okay. And the only external force is due to gravity. And okay, let me just actually write nice English. And the only external force is gravitational force, is due to gravity. Now, I'm not a physics dude, so bear with me. We are being asked to find a position function. R of t of the projectile. Right? And we also ask what value of alpha maximizes the range. So what alpha maximizes range? And when we talk about range, we actually, in this case, we talk about the horizontal distance. So that's confusing in math terms, right? Because we're used to seeing horizontal distance as domain, right? And vertical as range. But here in this case, it's reversed. So horizontal distance traveled. So a lot of wording here. So basically the idea is we're given a scenario, we fire a projectile given an angle and an initial velocity vector, and we assume there's no air resistance except gravity, and we find a position function r of t of the projectile. And we also find an alpha that maximizes our horizontal distance traveled. So when we talk about maximizing, we talk about optimization. So probably something to do with derivatives again. Okay. So let's set up a solution here. So we set up the axes, so both the x and y axis, so that the projectile starts at the origin, right? So we start here at the origin. And what else can we say? We can say that since the force due to gravity, or the gravitational force, actually acts downward, then we can use Newton's second law of motion, right? So we say that since, I'll just write gravitational force acts downward, then we have F is equal to ma. F is force, m is mass of that particular projectile, and a is, well, acceleration vector. And here we say that F is a vector, right? This thing is a vector. A is also a vector. That's our acceleration vector. And here we further contextualize this. We say negative mgj. Why did we say that? Well, where did the negative, the g, and the j come from? It actually came from our acceleration, right? So let me just complete the statement here. So here we say where g, okay, so let's do g. G is basically the absolute value of A, right? And that absolute value is approximately 9.8 meters per second squared. This is our acceleration due to gravity in physics. Yeah, and and we also say that A, our A vector, right, is equal to negative gj. Or in other words, it's 0 negative g, right? Because what's happening here is if we take a look, well, we're not moving in any x direction, but we're moving in some y direction downward. Something like that. That's our gravity, right? It's like what? Pulling us down, so that we won't escape Earth. But yeah, that's the idea of that vector. Okay, what else? Okay, we also said that, or we also say, not said, that the derivative of my velocity vector is my acceleration, right? That's true. Then that means my actual velocity is what? Is there like probably like an answer key here or something? Okay, there's like a couple of stuff here. So here I would probably write like a v of 0. Yeah, there's like a fill in the blanks thing here. We have v of t is equal to blank plus c, where c is the initial velocity. What in the world is this? Honestly, the first thing I thought of was integrating my acceleration vector. And so that means I integrate this. Mm, yeah, that's what I was initially thinking. I mean, I know I did this one before, and it was definitely a tricky one. Where were you? Something about projectile motion. Oh, there we go. There it is. Yeah, this is in the textbook. Oh, so it's negative GTJ plus its initial velocity. I think that's what it wants me to put, no? Oh, there we are. Negative GTJ plus C, where C is the initial velocity. Where in the world did I get negative GTJ? We actually integrated it. That's what happened. Yeah, that's what happened. So the idea was to integrate. Okay, let me complete this. To integrate my acceleration vector. And so that means I want to integrate its components, right? So I want to integrate 0 dt as well as negative gt, not gt, negative g dt. Okay, let me put it in a separate. Uh, and apparently it wants it in ijk form. I don't like working in ijk form. And then from here, well, we just integrate it, right? So here we got 0, here we got negative g d plus some constant that we don't know. But actually, we do know. Because if we integrate this, we put our g out, 1, we make it a t, we get some constant c1, I don't know, and we plug in where v of 0 is actually what? My initial velocity. And my initial velocity in this case was this thing here. So it's just time. Oh, I'm not gonna dive into it too much. It's just that. Now, vector-wise, this is confusing to look at. um, but yeah, it's that. Let me just say this is C. So plus some constant that we don't know. And we can just translate it to its ijk values here. Right? This C is just some constant. I could write it like this. I could write it like this. What's this constant? Oh crap. It's just a constant. You treat it as a constant. This times this is just some number that we don't know. So we just treat it like a constant. And so this constant is again when v is or when our parameter is 0, we get v naught. Right? And so that yeah, I mean that's what it wants us to do, if I'm not mistaken. Yeah, so it's just negative gt, and then we put the vector j here in this case. So I hope we got that. I hope. Okay, never. Let's. Yeah, yeah. We're gonna keep going on. Keep going on. We're gonna keep going. Where am I? Okay, there. Okay, let's say hypothetically we got this. I want to go through all of them first. And then if we integrate it again, right? So integrating again. It's like a fill in the blank thing. we obtain r of t. So if we integrate our velocity vector, we obtain our position vector. Now it's not erasing. I'm just showing how integrating it turns into its velocity vector. Oh no, it's position vector. And now what do we get? Okay, let me actually complete my solution here. So I'm going to integrate my v of t dt. And so that means I integrate its components, right? So I integrate, well, my zero is just zero. Then I integrate this thing. Yeah. So how does that work? Well, I would just integrate this thing in and see where it goes, right? Yeah, I would probably just like what? Like do this, like that, and then just see where it goes. The letters are making it confusing because I don't know which one's a vector and which one isn't. Okay. Let me just double check what I did here. Oh, now I got n squared, yeah. And I put the d here. Okay, that makes sense, yeah. Yeah, yeah. Because when I integrate this, I put squared over 2, right? And so I get like what? Negative 1/2 gt squared. And then this one, my v naught, if I treat it like a number, I get a v naught times t. So that's something, yeah, I mean, yeah, that's what I would get. But then the funny thing here is, also I integrated with j. So it's like, okay, so I think my technique here is like, I don't even care what that j is. I just do it. And like, I don't care. So I just go for it. So I'm like, okay, let me just go for it real quick. I integrate this, and I get something like negative 1/2 gt squared plus t v naught. So I get something like that. So here I pretty much don't care what that j is. Okay, actually I need to put the j here. There we go. Now, do I add a constant? Of course I do. Let's do what? The text box says, or my thing says d, so I'm gonna just add it there. Okay, it's a bit long. That's fine. Okay. And here we say that d is actually d is a vector. What? R of 0, which is equal to 0. So my d is 0. And so the position vector, oh, R of d is just this thing here without even the. So here I just completely take out my d, I mean. And that's it. Okay. And then what else can we say? Did I get that? Okay, I hope I got that. Actually, let me write all of what I just did here. So I put negative 1/2 gt squared, and then I put my standard basis vector. I put my j here. I put plus t. So here I just put t. And I do the same thing. I add my j, and this j is again a standard basis vector. And I put t. Cool. Okay, and now if we, what is this? Okay, Now, if we write, so this is my vector, my initial vector, right? It's just actually equal to my, I'm assuming this is speed, right? Yeah. There's no way to distinguish. So I'm just gonna write an arrow if it's the velocity. Just so that indicates direction, right? Because that's what the velocity is in physics. That one I remember. Okay, what am I saying here? Oh, so now I have to find this vector. I have to find this thing. What is this? So I have something in I plus a V naught sine alpha J. What's in my I? I mean, I don't know, if I look here, I see something. It's moving. Did I put anything in terms of I? Maybe a past information I could use. Integrating R if the it doesn't, because these are J's. What did I do in the previous one? Uh, oh, I put a cosine. Okay, pretty sure this is just a physics thing. That makes it super iffy. Yeah. So something about angles and relating it to, yeah, I mean, it's a physics thing. Yeah, so yeah, it would just be V naught cosine alpha, pretty much, right? V naught sine alpha I plus my V naught sine alpha J. It's just, it's just a physics thing. Um, yeah. Then yeah, equation one becomes my R of t. So V naught cosine alpha t. So now I multiply it by a t. Because I want to parameterize it. And at the same time, I also do it for my j or my y component. Yeah. Then now I have parametric equations. Whew. Okay. There's a way I could understand this completely. Yeah, I'm not a physics guy. Um, the J's are confusing me as yeah, these are general formula. Yeah, these are general formulas. But I can understand why it's like alpha and sine, right? For my velocity vector here. Because I just do this. I have a right angle there. And then I say, what's cosine of alpha? Well, cosine of alpha is this side, the adjacent side over its hypotenuse. This adjacent side is what? Is my change in x. So some change in x, and then this is my velocity. And so I'm saying that my change in x is equal to v naught cosine alpha. Right? So I'm saying that this change here is v naught cosine alpha. And I just added t because I want to parameterize it. I want to know at what t am I at. So if I'm at t equals 1, maybe I'm here. That's my x value, my change in x, or my v naught cosine alpha change, right? And then it's the same thing for my sine. So it's really just trig stuff. So I get that. Um, okay, maybe I get a bit, just a bit. Okay, cool. Now we have an equation. So now we have R of t here, which is my x, my change x, But then I multiply a t here. Then I have my I. So now I parameterize it in terms of t. Then I add my v naught sine alpha. And then this is also in terms of t. And then I subtract, right? So here I subtract 1/2 gt squared. So I got this from, if I'm not mistaken, I got it from here, right? So here, where did I replace it? I replaced this thing here with this. I added the sine alpha because I want to consider the angle this time, right? Okay. And then from there, I have parametric equations in terms of alpha and d. Yeah, these are just position equations to help me determine where I'm at in terms of x and y. So I have parametric equations in this case. Okay, I went through this like what, 3 times, and at least I'm getting it bit by bit. But during my first time, I can't do it. So x is what? X is v naught, and I think this was cosine. Okay, I'll put the bracket now. Cosine alpha, and then I multiply it with a t to parameterize it. Then my y is v naught, and then now this is sine alpha. And then t, and then here I subtract it with my 1/2 gt squared. And then my horizontal distance, right? Because I want to maximize my alpha. So my horizontal distance, I'm gonna say it's d. So let me just assign that. I'm gonna say it's d is x when my y is 0, right? Because when I set y to 0, I get a t value for it. Yeah. So and so when we set y to 0, we actually obtain t equals 0. Right? If I set this thing to 0, oh crap. Then I get t equals 0. That's weird because I have like 2 things here. At least I know my g, but I don't know my t and my alpha. Or can I assume my alpha is something? What did I do there? I actually forgot what I did. Oh, there we go. So we set y equal to 0. We obtain t equals 0. Was there an initial condition somewhere? I probably solved it somewhere. Maybe I solved it. Let me actually see. Let's solve it here. So I didn't solve it in the previous one, so I'll solve it here. I'll put like complete solutions maybe. And then here I'm trying to find the value of t. Yeah, you're right. I mean, yeah, I can just plug this in, make it a 0, right? So I could say, yes, t is equal to 0. T could be a 0, right? What else can we do? Yeah, I mean, I can factor out my t here, so I could say like what? How did I do this? Oh, I know I did. I probably just switched it up. So I made like what? 1/2 gt squared. Okay, let me solve it my way. Like this. And I get v naught sine alpha times t. I can divide both sides by d, right? So oh, there we go. I get this. GT2. I get that. And from there, I can just multiply 2 over g. So d is actually just 2 of this divided by g. Or d is equal to 0. So I could do it in either way. Okay, so I did solve for it before. Okay. Nice. Okay, I'm gonna keep the solution there because I forgot to keep it before in that previous video. Then we're gonna use that second value of t. Okay, not second value. We're gonna use this value here just to make it as general as we can. So here we say, okay, my d is just my x when what? V naught cosine alpha times t. And I multiply it to this thing here. So V naught cosine alpha times t. So I do V naught sine alpha over g, right? I just plugged it in. I think that's it, right? Oops. Okay. Yeah. Am I right? Let me just double check. Yeah, I'm right. This should be correct. If I'm following the formula correctly. And okay, let me continue. So this is what? World? What happened here? Oh, so now it. Oh, okay. So I did do V naught squared because I have like I have two V naughts here, and I did cosine alpha times sine alpha, and we talked about that before. We got 1/2 sine 2 alpha over g. And so from here, we actually just get what? Well, we can cancel these out. So we get V naught squared sine 2 alpha over g. It's a derivation formula thing. And clearly we see that d has its maximum value when sine 2 alpha is equal to 1. So again, how do we find when something has a maximum? Well, we take its derivative, right? And then we set it to 0. That's usually the task here. But I have like what? 3 unknowns here. G is a constant. V naught. What am I plugging this in for? Am I plugging it in terms of like what? Is it saying what's it saying? Maximum. Let me see if I can actually get this. If I can wrap my head around it. Maximizes the range. It would have been nice if we had like what a function that describes all of these, and I could find like a derivative or something. Okay, but yeah, D has its max value when sine of 2 alpha is equal to 1. I can see that in a trigonometric perspective, because if I look at the unit circle and I say my sine of something should be a 1, should be here. I think it was like a sine of 0, if I'm not mistaken. Well, not sine of 0. Sine of pi half is one of them. Sine of 19, maybe? Yeah. So it's when this is pi half or negative pi half. And then my sine of that is 1, right? What does that tell us? Well, that tells us that my y value is 0. So actually, my max value is when my y value is 0. That's what it's trying to say. Because that's where I would get a 1. So let me just... Basically, when my y is 0, that's the max value of alpha. And so here I just solve for it, and I get an alpha of 45 degrees. Pretty much. But yeah. Okay. So that was I have to do like I'm pretty sure, yeah, my professor did like a video on that. I'm definitely gonna watch it because I want to see where I messed up. But anyway, yeah, this was in the textbook, so I was a bit familiar with how it goes. Okay, so okay, V naught. What in the world was my V naught? Yeah, this was supposed to be cosine alpha, right? Cosine of, I think it was a trig thing. No, Greek thing. Trig, no, Greek. Cosine alpha. I had a V naught there. Oh, that's not. Still not? Is that how I added? I don't know if that's how you added. Okay, I'm gonna see if that's how you added. Okay. And then my horizontal distance here, and then my d is equal to V naught cosine alpha. So I basically just copy paste this thing. Okay. I'm just filling in everything in the homework. What? What's this? I simplified it. Do sine. Can I just say sine alpha? Or let me just do that. Let me see if it works. Should work, right? Oh, it wants me to say something about it. Yeah, it wants me to do uh, uh cosine alpha and sine alpha. That's what it wants me to do. Cosine alpha, sine alpha. That way, if I multiply those two, I get a 1/2. Yeah. Let me say something about 1/2. Is that it? That's not 1/2. I meant 2. Yeah. Because if I multiply, I get 1/2. Okay, cool. And this is 45. Can I put degrees somewhere? I can't put degrees, can I? This is degrees. Here we go. Okay, I'm not gonna expect something, but we'll see. Should be correct though, I hope. No, that's totally all right. Oh, shoot, got it. Okay. Okay, last one. I think this one's probably the hardest, just by the looks of it. Yeah, I'm definitely gonna go over that problem again. I might make a video out of it, maybe. Okay, so here we see that a ball is thrown east into the air from origin, in the direction of positive x-axis. I don't need to know that. Initial velocity. Okay, let me write that out. Let's say v naught prime. Maybe I'll put in a different paragraph, different line. The initial velocity 50, 48. Oh, 50, 0, 48. So that's it in vector form with speed measured in feet per second. Okay, cool. The spin of the ball results in a southward acceleration. So let me just write that. Ball spin results southward acceleration. So when we're saying south, we're going down. We have an acceleration vector here. Now, I don't know where he got the 48 thing, but cool. I'm going to translate it immediately to math. So a of t as 0 for my x, negative 4j for my y, and why is it I put j? Negative 4, negative 32. Okay, these look like nice numbers. Oh, where does the ball land? So I round my answers. Blank feet from the origin at an angle of blank from the eastern direction. So here I'm asking where does it land? So I need to use my parametric equations of projectile motion. So I have to make use of that. Which I think I derived it here, right? Did I derive it? Oh, there you are. Let me just make use of this. So where does it land? Oh, but then it's in 3D. Oh, crap. Okay. So I actually can't use this because this is only in 2D. Yeah, it's only in 2D. That's funny. Okay. Okay, I guess I don't know. I can try to figure it out though. So where does it land? It's asking for something in feet from the origin. And an angle. So maybe like how it was thrown, at what angle. That's my guess. And it was asking what speed. So maybe my position vector. So I can't make use of. I can't make. I'm only given like 3 things here. Initial velocity, thrown east, ball spin. I'm not given a function, so I can't really. Oh, why I say a of t when I'm not even given a number? It's not a of t. I would just say like a vector. Where does the ball land? With what speed in feet per second does it hit the ground? Okay, I give up. I don't know. Just a waste of time to try to figure it out. How do you figure this? Okay, so the first thing it says was to integrate my. Okay, we can try. Why not? Let's try integrating my acceleration vector. Let's do that real quick. If I integrate this thing, what do I get? Oh, now I get a function, right? So that means if I will get some function of t if I manage to integrate my acceleration vector. So I integrate each of these guys over here. Oh, look at that. I get parameters. And I even have a, but I don't know what time. Oh no, I do know what time. I actually do know what time this is. This is v of 0, right? Okay, we're getting somewhere. East from the origin. So my r of 0, 0 is actually just, okay, I figured it out. I think. I'm also gonna check the solution while I do it. But basically here I integrate. This is just 0. This is negative 40. Okay, let me do it one by one maybe. This is 0. But I add a t. So that's still a 0. It doesn't matter. I add a c1, which is 50. Right? And so from here, I can automatically just do it. My c1 is 50. And then negative or, oops, I integrated immediately. So you have negative 40 plus c2. And I get the constant immediately. I get 0 here. I plug in the 0 here, right? So I immediately plug in this thing. I get a 0. So my C2 is just a 0. Then lastly, I do the same thing here. Is it a minus? Yeah, it was a minus. I have a negative 32. Yeah, and here I do the same thing. My bad. Dang, it's one of these moments where I'm like, oh, it clicked. Okay. I plug in my 0 here, C3, and this is what? 48. And this makes sense because this is the initial velocity at time equals 0. So we're definitely going to cancel out all of those parameters. So yeah, here my C3 is just 48. So now we do have a velocity vector that we can work with. So it's C1. Now this is forever 50. Yeah, because this one's a 0. What else? This one's negative 40. That's a 0. And this one's negative 32t plus a 48. Right? Great, we figured that out. Now we integrate that again. To get our position vector. Do we want that? Oh shoot, I don't know what it's asking for. Where does the ball land? Okay, let me do that after. What's the next one? What speed? Uh, what speed does the ball hit the ground? What speed? Well, this one's just like what? We find the time. Yeah, first we find that time where the ball when the ball lands. So that's also something we need to find. Then we plug that in when we take the magnitude of our velocity vector. We plug that time in and we get a speed. So that's good. Am I doing it right though? Because I feel like I might mess something up. Yeah, we integrate. It's cool. What else? Okay, I think it's, oh, okay, so now, yeah. So now I also integrate my VFT to get my position vector, because that's what I need. So my position vector here is R of t. So meaning I integrate my VFT. And here I say, oh, I integrate each of my components. Okay. Then from here I say, we do it one by one. So here we get 50t, and I add C1, and this is equal to what? Well, here we're given the condition that, okay, I'm just gonna write it. So given that R of 0 is the origin, right? How do I know that? It doesn't say there. What? Oh, a ball is thrown eastward into the air from the origin. So that was the starting point, from the origin. Oh, no, it says it here. So at t equals 0, the ball is at the origin. That's how I got this info. Now I just set these to 0. C1 is 0. Let's do the same thing. Oops. Here we, oh, now this one becomes t squared. This becomes negative 2. T squared. Yeah, because negative 4, t squared over 2. Cool. Okay, then we add some constant again. Let's call it C2. Here we multiply it by a 0 squared. So here my C2 is also squared, is also 0. And then lastly, we do what? 40, oh, negative 32t plus 48. dt. And this is equal to, so if I integrate it, right? 32 over 2, that's 16. So I get negative 16 here, t squared. Then here I get 48t, and I get some constant. Okay, and I substitute everything with 0. I equate them to 0. And so yeah, C3 is just 0. And so my R of t in this case is just the vector with 50t, negative 2t squared, negative 16t squared plus 48t. Lots of t's here in this case. Okay. So now, what do we need to do? Well, okay, we need to find where the ball lands. So where does the ball land? So where does it land? Well, it lands when my position, right? My R of t is at 0, 0, 0. That's where it lands. My x is 0, oh actually no. My z is 0. If I'm treating it as if I'm treating my xy plane as a ground, is it safe to assume that? Okay, let me watch it just to be sure. So I get my R of t. Also, it is. So we're treating, so where does the ball land? We kind of assume here that the XY plane is the ground. So that's what we assume here. So the ball hits it. When it intersects the XY plane. So when Z is 0. So we're saying that when negative 16t squared plus 48t is equal to 0. And here we just find a t that works, right? Now let me quickly, can I, oh, okay, lucky. So I can divide everything. I can divide everything by 16. So I get negative 3t squared plus t is equal to 0. I think it was the other way around. uh, yeah, so I have negative t squared plus 3t is equal to 0, right? And then from there, I can factor out the t maybe. I can say 3 minus t. Oh, look at that. My t could be 0, or my t could be 3. So obviously it's when t equals 3. Because this is where, so this is when ball hits ground. How do I know? Well, when t equals 0, that's where it was being thrown. That's at the origin. But when t is 3, that's when it hits the ground. Okay, so the idea here was to, I want to, so here I want to find the time. So now I'm assuming my parameter t is time. So those are the two assumptions I made in this problem. My assumption is that the xy plane is the ground. So that means z is 0. And my t is a time. My parameter t is a time. When ball hits ground. So there are only 2 times here. So we solved for it. There are only 2 times here where the ball intersects the ground. Whether it starts, they throw the ball, or whether it hits the ground. So it doesn't. Yeah. Okay. Now we found t of 3. Now we can actually find the exact coordinates on where the ball landed. Right? So we can do that. So if I try to, okay, so find, so it's not asking for the coordinates actually. It's asking at what feet from the origin. So here I'm asking find the distance of ball from origin when it hits the ground. So that's what it's trying to find. It's not actually trying to find the coordinates, but we're gonna have to do that. And then we're just gonna use a distance formula. That's what we're gonna do. So okay, let's quickly do that actually. So let me use my position vector. So at r of 3, I get what? Let me just actually manually compute this. So I get 50 times 3, I get 150. Let's make it complete actually. Yeah, let's just go for it. We say 50 t. I'm assuming, oh no, it's not squared. Okay. So here we say 50 times 3, comma. Here we say negative 2, 3 squared, comma. And then here we say negative 16. 3 squared minus, I subtract, oh no, I added with 48 times 3. And from there, I should get a number. So I get 150 for my x component. I get negative 18 for my y component. And I get, what's this? 16 times 9. Let me just, it was negative 144. I add it to 144. Oh, I get a 0. Cool. Yeah, that makes sense. Because yeah, we hit it at 0. Okay. I don't even know why I computed for that. Maybe just to make sure. Okay. Now we find the distance of this point, right? Towards the origin. So we basically do a distance and we equate it to, I don't know, this one here. And 0 squared, we might as well include it. Why not? So distance, let's just say from origin. Here we got like what? 150 squared. 22, let me just write it out. 22500, we added the 18 squared. You know, this is the only time I actually use a calculator when there's long computations like this. 22824. Oh crap, did I? Oh no. Yeah, this is a 2. 22824. Let me see. 2253824. Okay. Yeah, can I get the square root of that? 22824. Oh, I can't. That's too bad. Do I approximate it here? Oh, so I do approximate it. So I get the square root, 22824. I approximate it to 1 decimal place here. So in this case, 151.1 feet. Done. That was a interesting problem. And now we're being asked at what angle. That's another thing. If I process right though, yeah, I get the 5. I plug it in my position vector. I get a corresponding vector with components. I find its distance. I approximate the distance. So to find the angle, well, yeah. So here I imagine something in 2D. Yeah. Uh, so to find the angle, well, I have to imagine something in 2D. My Y, my X. Let's say this is my origin, right? We're at the ground. Was it? Yeah, because it was just asking for eastward direction towards the south. So I just need to imagine something in 2D. I have my 0, 0. And then the point at which it landed was 150 minus 18. Like what? Like here maybe? Towards here. That's just a guess. This is the angle it was thrown. We'll call it theta. And this is what we're trying to find. And I'm pretty sure it's asking for it in degrees. So we're gonna say in degrees here. So to find that angle, well, what do we know? We know this distance, right? That's square root of 22824. What else do we know? We know this is 180. Oh, 180. 150. And we also know this is 18. So lots of possible ways to find to find our angle. We just need one of them. Right? We can get a tangent. I think that one's the easiest. Yeah. So one relationship we can say is, okay, let me do it another way. Let me look at it in a different way. So here we say something that turns into this. I have my theta here. Here was, this is 150. This is 18. This is square root of, I mean, you can do a Pythagorean theorem to see if it matches. This is 22824. Let me actually do it real quick. I'm curious. I'm actually curious. 15 150 squared plus 8 squared. Yeah, I got 22824. Yeah. So this is a right triangle. It's a perfect Pythagorean theorem. And then what happens is we find this angle. We basically use anything here. I'm just gonna use tangent. Tangent of theta. And we get something out of it. So the opposite side over its adjacent side. Yeah. And so my angle is just the arctangent of that. And I can approximate it to something in degrees. Yeah. Can I? Oh, so there is a number, 0.12. I'm in degree mode. Arctangent of 0.12. Huh, really? I mean, 18 divided by 50. Yeah, it's around like what? This is in degrees, right? Or my eyes are blind. 6.1 decimal place, 6.8? 6.8 degrees. Should be that. Sounds really low. Okay. Should be fine. I'm trying to look at his example. Okay, so you did get something similar. Okay, now we want to find the speed. Well, here we just plug in what we know. Right? So we find so we find the speed at which the ball hits the ground. So find speed when ball hits ground. So what was that speed? We get the absolute value of my velocity vector. Do I still have that? I should have it somewhere. There you are. So we get the absolute value of my velocity vector at 3. Right? Okay, let me just solve for v of 3 real quick. So v of 3, what are the numbers? 50 minus 40. I just plug in a 3 here. And I think this was minus 32 if I'm not mistaken. Yeah, minus 32 plus 48. Minus 32t plus 48. And I should get a number here. I got 50. I got negative 12. 48 minus 96. Negative 48. There we go. Now I find my distance here. So square everything. And boom, we're done. I can simplify. This is 2, 5. This is 1, 4, 4. This is 2, 3, 0, 4. Continue adding. I get 4, 9, 4, 8. I get the square root of that. That number is kind of. Do I approximate again? Yeah, I do approximate. So I get 70.3 feet per second. Whew. Okay, I'm expecting this video to be super long. I don't know I was gonna take so long in these problems, but yeah, really there's a lot of things that can be done with velocity, with acceleration, with speed, basically with motion. Anything that moves. I mean, that's calculus at its core, right? It's the study of change. We analyze how change happens. And one change that we analyze just happens to be this idea of motion or how things move. So yeah, pretty cool stuff. Okay, before I give an ultimatum, I'm kidding. Let me look at my answers. Okay, now let me pray to see if this works. Okay, got it. Nice. Okay. Yeah. So back to what I was saying. Really, the idea here is we're analyzing how change happens. Like we're finding how the ball hits the ground, when it hits the ground, at what speed was it when it hits the ground. We find the distance of the ball from the origin, stuff like that. We also did like projectile motions here. Uh, we did we analyzed a bit more of what exactly is acceleration. So we looked at its tangential and normal components. Uh, Mostly these other ones are just really plugging in and getting used to the formulas. But the idea is there. The idea is there. Uh, yeah. Anyways, I hope you guys enjoyed. And yeah, I'll see you all in the next video. Thanks, guys.